this community. Shall I start? Do you want to start the recording?
Yes, I start the recording, so go for it.
All right. All right, so I'm going to talk about fairness and explainability in robot motion, which are probably concepts that one wouldn't think would be relevant to robot motion at the first instance, maybe, but I hope to convince you otherwise. So for those of you who are not familiar with path and motion planning, these are technical problems that are very important in robotics, but not only robotics, even in your phone apps when you ask to go to a certain place on your GPS using Google Maps or something. You have to solve a path planning problem. So to find a sequence of steps over a network of roads, for example, to get to the goal. And the motion planning problem is the continuous version of that, so where you want to find, for example, full body postures of a robot. So exactly where each of its motors should be and its position in the world should be. And this is both for this kind of robots with an arm and the wheels, or humanoid robots that need to do steps and avoid obstacles and balance and etc. Legged robots, but also autonomous vehicles when you want to find a trajectory maybe for the next 10 seconds that avoids obstacles, so is safe, but also perhaps is smooth and comfortable for the passengers. And even in warehouse automation, so computing the paths or motion for many of these robots to reach their destinations without colliding with each other, and making sure they satisfy certain constraints. So this is the path and motion planning problem. I'll start with the explainability of robot motion. So to try and unpack this concept of explainability, I'm going to start basing myself on some literature review and some user studies to arrive at some working concepts of what could explanations for robot motion look like, but then use the actually implement concrete explanation generation algorithms or explainable planners and get feedback from users to iterate the concepts and figure out what are the important design considerations when thinking about explanations for robot motion. So why would you actually want to explain the way a robot is moving, or the output of a motion planner? So here are two examples. Your robot might move in a way that you did not expect. So for example, here this robot is taking this long path through the right around the table to reach for a shelf. And the operator or the user might think, why are you doing such a long path? You might be spending more battery than you should. I would expect that you or the robot would take this other path that is shorter through the other side of the table. And another reason is that sometimes, or actually very often, planning algorithms just cannot find a solution. So they'll tell you, yeah, sorry, I could not find a solution after I tried for so long, or I was unable to solve this planning problem. So I cannot get the robot to where you want it to be. And then the user or even the developer is left with no clue as to what they should do to fix this issue. Why is it failing? So I've actually recently done a user study with both developers of motion planning algorithms and expert users who use it on a daily basis of motion planning algorithms. And most of them, kind of the recurring theme and opinion was that explanations could be useful specifically for debugging of these algorithms and also for mechanical design, for iterating the mechanical designs of robots. So these experts, these were around 20 or 25 experts. They were commonly saying things like explanations could accelerate the debugging process, or they could even help the developers understand the inner workings of motion planners, because even though they develop the algorithms themselves, often it's not intuitive, the outputs you get. Why is it that the output is the way it is? So sometimes the expectations of developers do not match the actual outputs of the algorithms. And explainability could even suggest algorithm changes, so things to change in the algorithm, such as to better match the expectations, or they could even suggest changes to the robot model, so basically the mechanical design of the robot, or morphology or actuation changes. So of course, this is the point of view of experts, and probably the different people will be interested in making different questions, and they will be interested in different kinds of answers when they ask questions about robots. So a developer, as I said, could ask questions about a certain plan that the robot has in order to make changes to the algorithm, improve the algorithm, or find a bug. But maybe a lay user could ask questions about what the robot is doing. Imagine a warehouse worker could ask questions about what the robot is doing in the warehouse in order to better understand how the planner works, to better be able to predict how the robot will move, and so better collaborate with the robot maybe. But the mechanical engineer might ask questions about the robot, might ask questions that are based on the robot design. So for example, why can't you reach for this object? And this maybe a mechanical engineer would like to hear something like, because my arm is not long enough. And so they will know that they should change the mechanical design of the arm. And even and an architect could ask questions in order to be able to change the layout of the warehouse, for example. So it depends on the user, of course. Then what kind of explanation? So what can explanations look like? Of course, this again will depend on who the user is and what they're interested in. But of course, there are also different ways to answer the same, different possible explanations for a certain question. So I've organized this into problem-centered explanations and algorithm-centered explanations in this recent paper. So if you see this example here on the right, where the robot does path A, but the user expected path B, so why is it that you took path A instead of B? The explanation could be based on costs, so because B would take more energy, or because of constraints, so because B would violate a certain constraint. B would actually be in collision. You don't really see it, but it would be in collision. Could be based on robot design because the robot cannot fit through corridor Y, so it's based on the dimensions of the robot, or based on the environment because there's an obstacle, there's a table in a certain location. On the other hand, there are algorithm-centered explanations. So you could say that the algorithm found path A, not B, because you didn't run the algorithm for long enough. If you had run it for long enough, it would have actually found B. Or because the algorithm is not optimal. So of course, there can be different explanations, and also similar explanations to these if you're wanting to explain failure. So now I have a kind of a set of working examples of possible explanations. And to better tease out what are the actual design considerations and how you should actually show these explanations, I went ahead and did some prototype implementations of these explanations. So one was the constraint-based explanation. So imagine your algorithm fails, so it cannot find a path for the robot to reach for this water tap here, for example, on the left. And I made an algorithm that automatically generates explanations for this kind of problems. So it will say, I couldn't find a solution because I cannot simultaneously touch the water tap or grasp the water tap and avoid collision, for example. Though I would be able to do this if the water tap was 15 centimeters closer, for example. And another kinds of explanation algorithm that I've done is based on initialization. So it's an algorithm-centered explanation. So you could say I failed to find a solution because the initialization, which is a kind of step of the planning algorithm, initialization was in the basin of attraction of an infeasible solution. Though you would have been able to find a solution if you had used a different strategy. So you could also say because you used this initialization strategy instead of the other one. So how I generate this kind of explanation is basically for this initialization, I just try a different kind of initialization scheme, initialization method. And if that works, I can blame the initialization scheme, basically say that's the reason. For constraint-based explanations, I basically solve many relaxed problems. So problems that do not need to satisfy all the constraints of the original problem. So they're sub-problems. And I try to find that problem that satisfies as many constraints as possible, so that is as close as possible to the original one. So I then showed these kind of explanations to the same expert users as before. And so, well, one good thing is that most of them were satisfied with explanations. So in this kind of question, like how much are you satisfied with this kind of explanation, 1 to 7? So they are in general they were satisfied with these kind of explanations. Some explanations more than others, but overall more satisfied than the kind of output they currently get from motion planners. On the other hand, I got some interesting insights, such as users were not sure as whether one should see, when there are multiple possible explanations, whether the user should see only one or a set or all possible explanations. So it could be the case that you could make a problem feasible both by saying that two constraints don't conflict, or by saying that you could change the initialization method, right? So which kind of things should we show, or should we show all the options? Another insight was that sometimes the language was hard to understand, potentially for lay users. So we might have to tune the kind of language that you use depending on the user. Other users complained that it was not clear to them why there was a collision. So even though the explanation was because there is a collision, it was not clear there was actually a collision. So visualization aids might be important to make things more interpretable and intuitive. But perhaps the most important insight from this user study was that many people said that explanations should go deeper. And for example, not just say, I couldn't find a solution because I can't reach for this and avoid collision at the same time, but actually say why it is that you cannot reach for this and satisfy collision at the same time. So for example, you could say, in this case, you should go deeper and say, well, you can the water tap is too further away from the beginning of the furniture. That's why you cannot solve this problem. So what should explanations look like then? The visualization theme was very common around this expert input. So they suggested we should use highlighting or visualizations of feasibility regions, etc., to improve interpretability, but also abstraction. So sometimes it's not enough just to say constraint 1 conflicts with constraint 2. You might have to use intuitive concepts. For example, say, because the environment is too cluttered, or because the object is not close enough. But these are very abstract things that we will have to find methods that this is, I think, an open problem, that we still have to find methods that are able to come up with these abstractions automatically. And finally, this deep explanations theme of, so not just say, because two tasks conflict, but to say why they conflict. So I then did another user study with a different kind of method. So this was not just a very simple method as the ones before, but a more involved one using advanced algorithms and more perhaps more visualization focused. So here you want to ask why. And I was also interested in seeing, so if explanations are actually effective at helping users understand the problem. So I wanted to evaluate this depending on the kinds of design choices you make. So for this specific problem, you see here there's a map with blue and red areas. The blue areas are easy to move on, and the red areas are hard to move on, so you have to go slower. And then the shortest path, or the fastest path, is the path A, which goes around this long distance, and path B is what user expected. And so the user asks, why did you take path A instead of path B, which is shorter, and takes these stairs here? This is a staircase. And so I've proposed some new algorithms to generate explanations for this kind of questions based on inverse shortest path algorithms, for those of you who are familiar. So basically what these algorithms do is to answer the question, why is path A optimal, not B? They find the minimal changes to make to the map so that the path B, so the user's expectation, would actually be true. Which means basically here you would say, well, path A is the shortest, not B. because for B to be shortest, the shortest, you would have to change the traversability or the ease of traversability of these two areas here. So you would have to make these staircases here be easier to traverse if you wanted this to be the shortest path. Or you could say because A is the shortest, not B, because walking on blue is too cheap. So if it costed a bit more to walk on blue, then B would actually be the shortest path. So you can automatically generate these kind of explanations. And even more recently, I've developed an algorithm that can even generate all possible optimal explanations for a question. So say, why is path A optimal, not B? And you could say, because for B to be the shortest path, the terrain should change in one of the following ways, and it gives the user all possible ways in which. So for example, if you put these two areas here, or these two, or these two, if they become hard to traverse, then indeed the shortest path would be the one you wanted. But since it's not that way, the shortest path is this one instead. Right, so I passed these explanations on to users, so another set of users. So single explanations and multiple explanations, and I've tried to see how well. So after seeing many of these explanations, do users become better at understanding and predicting the behavior of this path planner? And there was some interesting insights that we got. So, for example, more user satisfaction does not mean that the explanations are more effective. We actually got the opposite. So people were more satisfied with one kind of explanations, the one with multiple options, but they actually got worse at understanding the problem if they had seen more possibilities. So it's also interesting that showing multiple possible explanations could actually be counterproductive and confuse the users and decrease problem understanding. So to kind of sum up, there are important design considerations to think about when you're implementing explainable planners. The type of explanation depends on user needs. There's a conflict between user satisfaction and understanding. Users might prefer simpler or more complex explanations, even though they're not as effective. There's a conflict between complexity and multiplicity, and you should also pay attention to explanation depth and visualization abstractions. But also kind of a general methodology that I used here, which was to explore a concept, an ethical concern of transparency or explainability, and jump into implementation of prototypes and use these to anticipate design issues and to actually refine the concepts and iterate. And this could be potentially a good, I believe this could be potentially a good tool for responsible innovation as well, which I will apply next to the problem of fairness in robot motion. But if there are any questions at this point about explainability, I'm happy to take questions.
Yeah, thank you, Martin. I see one question from Yi Young. Maybe if you can unmute yourself and ask the question, that would be great.
Yes, thanks. So thank you, Martin, for sharing your research. So my question is really about these constraints that you're describing, right? So it looks like you mainly consider those constraints that can be formally specified, right? And then you inject that somehow into your optimization algorithm. So my question is, are there constraints that are more ambiguous that need to be and that can only be expressed through, for example, natural language or something like that?
Maybe so. Certainly, it's very difficult to in many problems. It's difficult to elicit the requirements, and it's difficult to understand what do we actually want the robot to do. But if we want the robot to do it using we actually need to formulate it, to put it down into an equation. So that's the only way it's going to work. But then So usually the way it works is that actually you start by eliciting the requirements of the problem, and then you implement it in a motion planner using specific equations, constraints, and then you deploy it, and very often you realize, oh wait, but the robot is still doing this, which is not really what I expected, so we need another constraint, and this often happens in deployment. So it takes a long time for you to get at a place where the robot is doing exactly what you wanted, and this is a continuous process as well.
Yeah, exactly. That part I found very interesting, right? It seems that what we do now is mostly, let's see how it works, and then we come back and maybe there are more constraints that we can derive, right? But then I'm wondering if there should be some, principled method that would allow us to get as much as possible in the beginning, and then of course it's an incremental process, right? We need always to test, to debug, and improve, right? So that's the part that I found quite interesting to share some thoughts.
Yeah.
And I do agree, right? For things to be usable by those machines, it needs to be formally specified. But then it would be really interesting to see what are the things that can really be formally specified and what are things that is hard, right? Maybe there can also be some research going on there.
Yeah. Of course, there are also methods based on learning, right? So if the user is not cannot easily write down the requirements, the users can just show examples, and then by seeing many examples, an algorithm could learn to do this. But this is impractical for large systems. Like, imagine a warehouse with 1,000 robots. The user cannot possibly have good intuition about how each of the robots should be moving. So you have to start by actually formalizing some objectives. So that's also just some thought.
Yeah, that's a good point. Thanks for sharing.
Yeah, and actually, as a follow-up to this question from me, Martin, so did you also consider, like, of course, you need to define all these constraints beforehand, but there's obviously going to be cases that you haven't foreseen when you started implementing or formalizing everything. So have you also considered scenarios where, for instance, the robot has no clue what, has not a real explanation and will just tell you, the human, hey, I have no idea what happened, but this is what all the events that led up to this point. And did you consider that in your algorithms too, or in your design?
No, not at this point. But so for example, it's usual for developers of motion planning algorithms to, for example, look at the search tree as a way to kind of get an intuition as to what happened. So the search tree is a kind of history of everything that the algorithm tried. And but I didn't, for example, compare the explanatory power of looking at the search tree versus these kind of explanations that I did here. So that would be a good baseline as well. Thanks for the suggestion.
Thanks. Yeah, interesting. Any other questions, or else we can move on to the second part?
Yeah.
Great.
Sure.
Awesome.
Okay. All right. So I'll continue then with the fairness, the idea of fairness in motion planning. So I'm going to use a similar kind of methodology that I used for drawing out this concept of explainability. So I'm going to try and start by actually simulating the deployment of a robot, and looking at the results and distributions of impact, and trying to understand what kind of issues of fairness could come up, and then directly formalize the concepts of fairness that are in the philosophy literature and distributive justice literature, and again simulate the deployment of a fair planner in those senses, and use those simulations to again draw out the design considerations and potential issues. And I'm going to suggest this could be again a good way to involve stakeholders in the process. So for all of this, I'm going to use a walkthrough use case to make things more intuitive. So this use case is of a rescue robot that needs to find as many people as possible. So it uses path planning or motion planning. So it starts at a certain point in the middle of a city, which is Oxford in the UK, the fire station. It goes some path around the city and then returns to recharge the batteries. And then, of course, we can use perhaps some census data about how the population is distributed, so population density or even age distribution and ethnicity distribution, to think about potential impact, but also about how to get as many people, find as many people as possible with our robot. So I'm going to use these simulations. I'm going to simulate a robot that is trying to find as many people as possible, and then look at the kind of which people the robot found and try and make claims about fairness in the paths of robots from this. So my first claim is that robot paths can be biased. Maybe this is straightforward to some of you, but the idea here is that if your robot tries to find as many people as possible, it should stay in the close vicinity of the launching station, both because it can then return very quickly when the battery is over, and because that's where the highest population density is. But at the same time, if you do this, the people you will find are mainly people in their 20s, so the undergraduate population of Oxford, and they're also mainly white, Chinese, and male. And these are the population you find if you stick to the center of Oxford because of historical reasons and because of the way the city works. At the same time, you can also make the other, the next step of claims, which is that robot paths can be discriminatory. So if you think that indirect discrimination is when a decision or policy, even though it doesn't target specific group, it has worse effects for those group. This happens in this case here, right? Because the people that are much younger, so the older population and younger population, are actually have less probability of being found by the robot, as well as the female group and minority ethnicity groups. Then you could go one step further and say that it's possible for robot paths to be unfair. So if you think that the goals of disaster response are to find as many people as possible, but also to attend those that are most at risk first, this strategy that tried to find as many people as possible actually did not meet the second requirement, because it found the student population in their 20s, which could be considered low risk. So you could say that robot paths could be unfair according to disaster response ethics. This other claim is perhaps also intuitive to many of you, but the idea is that robots must face dilemmas already faced by humans. So disaster response teams already have to think about the impact and the fairness of a mission. So the robots that are deployed for disaster response will, of course, also have to think about this. But how do we operationalize similar fairness sensitivity? So this is the step where I dive into implementation directly to try to tease out issues and design considerations. So I did a survey of the distributive justice and political philosophy literature and tried to bring these concepts and formalize them for the context of path planning. So here are 3 examples that are in this paper, in my recent paper. So demographic parity is one conception of fairness, where you say that the probability of the distribution of people that your robot finds in its path should be the same as the distribution of people of the whole city. So this means basically that when your robot goes and looks for as many people as possible, it should still try to pick a representative sample of the population of the whole city. But there are also conceptions of fairness, for example, that the distribution of people found by the robot should be such that all groups have at least a certain probability of being found. This is a sufficientarian approach. And it could also be a Rawlsian approach. So the path should maximize the probability of the least likely group. And there are also other kinds of fairness conceptions, of course, but I'm going to stick to one and try and tease out possible issues that come up when you choose a definition of fairness. So I implemented a motion planner that simultaneously optimized the number of people found and minimize the unfairness. So try to get the distribution of people found by the robot as close as possible to the distribution of people of the whole city. So this curve here has many points. Each point is a different path that the robot could take. And this point here more to the left says 0.6. This 0.06, this is the distance to the ideal distribution. So if this was 0, that would mean that you could find a path that had the exact ideal probability distribution. So you can already take quite a few. So if you're interested in the details of the method, you feel free to read the paper. It's a Pareto estimation method. But independent of that, so you can already take some interesting conclusions from here. So first, it might be not possible, not even possible to satisfy a fairness definition exactly, which is the case in this example. So this never reaches 0. And to find more people, you might have to compromise on fairness. So to find more people, you might have to find people that are less representative of your city in this short path. Another observation that I made in this work was that a fairness definition could be counterproductive. So here is the comparison of two fairness definitions. One, which is demographic parity. So your planner is trying to, as much as possible, that the path finds male and female groups in the same proportion as in the whole city. And this in the graph on the right is the result of running a planner that tries to promote affirmative action. So exactly 50% ratio of men and women found on each of its paths. But you see that when you do the algorithm on the right, you find both fewer men and fewer women than if you apply the first definition of fairness. So you have to be careful. You cannot just think, oh, I think I should implement this fairness definition, not that one. You might have to actually simulate it to see what happens, because it might even be counterproductive, be worse in all respects compared to another metric. So a kind of final, more technical conclusion or observation is that current methods for motion planning offer a few guarantees. So basically, they're methods that will solve your problem optimally, but you'll have to make an approximation of the problem. And there are methods that will try to solve exactly what you asked it to solve, but they cannot guarantee that they will do it optimally. So you have to choose between optimizing the real fairness, in quotes, fairness metric suboptimally, or optimizing something else that is not what you care about optimally. So intuitively, for those of you who are familiar with the A-star algorithm, for example, for path planning, you have to use a cumulative cost, which means that the cost of being in each cell along a path is equal to in this case, it would be equal to how close the distribution of people on that area is to the distribution of people over the whole city. But this would mean that your planner would try and avoid neighborhoods that have minority neighborhoods, because they are not representative of the whole city. So even though you're trying to optimally solve a fair planning problem, you're actually doing something very unfair, which is to avoid minority neighborhoods, because they're not representative of the whole city, because of the approximation that you need to use in order to apply an optimal planner. All right, so you can complain about this toy example that I did, that it's not realistic enough, because it only does one path and returns, and that's it. So I've recently started exploring the coverage problem, which is when your robot will do a short path, covers a small area, returns, and then another area returns until the whole city is covered. It's called the coverage problem. And I've actually observed through experiments that if you're solving a coverage problem, again, trying to first go to the neighborhoods that have the most amount of people, so as to find more people faster. So you'll have this kind of graph for the amount of people you find. First, you find a lot of people very quickly, and then it starts slowing down the amount of people you find until you find everyone. But that also means that, again, you have similar inequality, and you have an inequality peak in the beginning. So in this particular example of Oxford, you would find 50% of the younger population by 200 minutes, but by 200 minutes, you would only have found 15% of the older population, which is a big gap, and also because the older population is potentially the one you care most about when you're doing these missions. So to kind of also take some conclusions from here, it's important to know that fairness can be not only about who gets served by a robot, but the order or the speed in which groups are served. We've also seen how population greedy algorithms, those algorithms that try to find as many people as possible or serve as many people as possible, will be biased according to structural biases in the city or in your domain. So this kind of bias could reinforce current inequalities and criticisms. For example, in disaster response, there are like from recent disaster response missions in the US and Thailand, there have been criticisms that the disaster response efforts did not help enough the marginalized groups, because even though they were from the start less likely to survive, and if we were to deploy this kind of algorithms for finding as many people as possible, we would again be reinforcing this kind of criticism, because we would not be serving marginalized groups as quickly as we should. So to sum up, in order to build fair robot motion planners, what we have to think about. So first I made the claim that robot motion can be biased and unfair. So this is both true for goal-directed and coverage paths. And I showed how motion can inherit spatial distribution biases of people. So people, they're naturally their segregations to that they're gentrified neighborhoods and their minority neighborhoods. So this is then passes to the motion planner. Then, of course, I omitted from the discussion here that there are also fairness issues related to census data itself and its representations and gathering methods, but I've kind of skipped that bit from this presentation. Regarding design considerations for fair planners, so I've shown how there's something to pay attention to is the fairness and efficiency trade-off, and I've shown how some fairness specifications might actually be counterproductive. And I've shown how there's an issue with the optimality of an algorithm and the use of approximations. And to wrap up in a similar note as to the explainability section. So how do we design for fairness? I think we need to iterate design and anticipation. And why? Because the set of personal characteristics we care about, or what we mean by fairness, the fairness specification, and the impact of a deployment, all of this is not obvious from the outset, so you might have to iterate. So deploy or simulate the deployment of a system, look at the results, and then iterate. And then another important aspect of this methodology that I used is that it is currently hard to engage with stakeholders in the early stages of design. So someone wants to deploy a robot, and they will say, yes, of course, we want to make sure this deployment is fair, but it's not clear how fairness even relates to robot motion, for example, right? So these discussions are also difficult to ground unless we have something palpable, like something like a simulation. So I think it's probably as a methodology, what I did here could be an interesting tool for a responsible innovation, where we implement prototypes and simulate deployment to anticipate issues with stakeholders and to ground discussions with stakeholders to better understand the concepts, so to iterate concepts and design considerations in the early stages of design. So thanks a lot for your time, and let me know if you have any other questions.
Great, thanks, Martin, for this really interesting talk. I see that Evgeny has his hand raised.
Yeah, thanks. Thanks, Martin, for the presentation. So about the fairness topic, so I understand that taking this perspective, if we assume that like a robot is introduced, that it allows us to uncover what kind of unfair dynamics might happen. But thinking more broadly about the ultimate purpose here, so shouldn't we be taking a more systemic design perspective here of the fairness issue? So what I mean by that is thinking more broadly about the infrastructure we are designing, rather than focusing just on the robots' decisions. So, for example, build more stations in different areas of the city, increasing battery capacity, increasing the number of charging stations throughout the city. So, thinking more broadly about what's the socio-technical infrastructure that needs to be in place to satisfy both of the objectives that you were saying. So also get to the people who are in need as quickly as possible, and make sure that you do that fairly.
Yes, I totally agree. I don't think what I talked here is kind of going against that thought. It would be a small piece of the puzzle. Of course, you need to think about how many robots you can use, how many to buy as many as possible. Where do you launch them from, and do you have the people to operate them? Is it even good to use robots in the first place? Do disaster response teams want to? Those are also important questions for the whole problem. So my claim here was more so first that there is a fairness component to motion, and then of course we should think of the whole system. So where to put launching stations, how many robots, etc. But then even then, so how should the robots move? Depending on how they move, it will still have a different impact. So it will still have a different, people will still be served or found or helped at different paces depending on the algorithm you implement. So regardless of that, we will still need this kind of algorithms and thought processes going into the design of motion planners. But I totally agree, yes, so that there's a lot of different problems to think about, and also more social problems of how are these then going to be used, and even how was this data obtained, and do the categories in the census even make sense? So these are all questions that need to be thought of. But of course, it cannot be just by myself. It would have to be a full interdisciplinary conversation with all the stakeholders. So in general, I really agree with what you say. Yeah. Thanks for the.
Thanks for clarifying that. And if I can, just a quick follow-up. You mentioned that you saw that it was difficult to engage with stakeholders early on the topic of fairness to understand the nuance better. Could you please elaborate on that a bit? Like what were some of the challenges in that?
No, so I didn't. So to clarify, I didn't actually do any user study with this fairness work yet. What I say is more a general claim, though I have no data for that. That once people who do not have so much knowledge about a planner or something or even the domain. So some people want to buy a robot to deploy in a hospital, for example, and they are aware that it's important, right? It's in the guidelines and the principles of ethical development of AI. Oh, yes, of course, we should make sure this is fair, but it's actually difficult to even come up with things you should have in mind when we will put a robot in the hospital or in the. What does it even mean for the motion to be fair? It's not clear how to even start the conversation. That's my issue. You can not start talking about compromises between enforcing fairness or not, or start talking about you cannot just use a menu of yes, do we want egalitarianism, sufficientarianism? Do we want prioritarianism? It's not just it's not easy like that to guide the conversation. You probably need examples, you need visualizations, you need simulations to tease out details of the definition. That's my claim, not something that I encountered personally.
Okay. Yeah. No, thanks for clarifying. Yeah. Now, because and of course if you actually do the empirical work, then of course if you start talking to people do not think necessarily like in our everyday conversations. We don't think in these categories, and we don't necessarily think in categories that align with quantitative fairness metrics that have been proposed so far in computer science literature.
Also true.
So that's kind of coming back to that first question I asked. Is basically the world is like the social reality is so nuanced that I think more broadly speaking, like we should be thinking about these socio-technical infrastructures where we figure out what's the appropriate roles for the humans to play to ensure, for example, fairness, but also explainability, what's appropriate roles for machines to play and the interaction between the two.
Yeah, I agree. Yeah, thanks for that.
Thank you. Thanks.
Luciano, you were first, I saw.
Yeah. Okay. So thank you very much for the talk. That was really great talk. And I really like the way you made very clear that explainability and fairness, they are relevant to specific concrete contexts. And that's very important to raise awareness that is like, we're not just developing robots, we're not developing just AI, there's things that are going to use in the world that have the impact. That was very nice, thanks. And my question goes on the aspect, on the second part, on the fairness, about the metrics and the definition. So it's basically following up a little bit on what you just comment here for Evgeny's question. It's because, yeah, indeed, people have like, it's not an easy thing to discuss about like what different concept of fairness, and also in broader sense, as you think about ethical AI, it should be utilitarian, should it be follow this Kantian approach, should we follow this or that? A way to try to see, to visualize, as I said, like through visualization, representations, and through demonstrations also as preferences. So because usually when people try to say, okay, I would prefer to go in this way or that way, and then you try to engage into this deliberative process, just saying, okay, why do you prefer this way than that way? Might be some interesting things there. So my question is going a little bit more to this technical side. So do you envision some kind of learning methods to engage these, for example, inverse reinforcement learning, or some approaches to try to learn what fair means for a specific group of people that might be impacted by the solution? So what do you think about this?
Personally, I'm not a big fan of learning-based approaches because you're never too sure what they're learning, and that's a kind of a personal approach. I think it's still perhaps easier to come up with rules that you totally understand, and then maybe iterate on those rules. But I think related to this learning approach, there's this kind of iterative planning approach that is popular in the planning community, which is when so you suggest, your algorithm suggests a plan, and then the user says, yes, but I would expect this to be, I don't know, fairer or more intuitive according to whatever it is that I think should happen. So the user provides some other suggestion, and then the algorithm could try to make that happen and say what are the potential issues with that. So show from similar to what I did in the explainability bits, either show that there's an increase in costs, or there's an increase in then this fairness metric would go down, or this minority group would not be seen anymore. So, and then by these back and forth, then the user, oh, I see, then why not this path? And then by this conversation, almost like a negotiation between planner and person, you could then arrive at a path. So even though it's not really the traditional learning scheme, it is still something similar, I think, in a broad sense.
Yeah, no, it does. And I just to clarify, I share your concerns with completely like open world learning approaches, which you don't really know, there's lack of transparency, lack of explainability there to the things. But I also see this value of this combining things. So you might have one specific definition of fairness, but by learning process, you can try to fine tune this according to interaction. So yeah, thanks. That was really nice. Thank you very much.
And also related to that learning approach, there also we could also think of methods that try and not just learn an arbitrary neural network or something, but come up with rules, explicit rules. So, then do you not mean this for fairness? What about this formula for fairness? Would that make sense to you? And perhaps always side by side with the examples of how that would work in practice. I don't know. Also, because in political philosophy and in these works about distributive fairness, it's always a lot about counterexamples, right? It's usually the rules sound perfect when you just look at the rules, but when you look at specific examples, you find counterexamples, and I think probably in design you'll have to do it the same way.
Yeah, definitely, and identifying which are the norms relevant, because I completely imagine that this path planning that we're going to work in Oxford maybe would not work in Delft and the other way around, right? So that's understanding what are the specific context-dependent norms. That's also very important. Nice.
Sure.
Okay. Thanks a lot.
Thanks.
I see we have 5 minutes left, and I see one more question from Arkady.
Yes. Hey, Martin. That was a fascinating talk. Thank you. I have let's make it 2 questions about the first part, about the explanations. And the first question is basically some of the approaches that you showed. It seems like there is an extra computational toll that you get on top of your normal motion planning if you need explanations. So can you comment on that? So I would imagine that some of them are more computationally intensive, some of them are kind of not as much, but in general, what is how hard is this trade-off between extra computational cost and explanation?
Right. Yeah. So in terms of computational cost, it depends a lot on the kind of explanation you want to make. All right. So maybe I'll share the screen at the same time. So, for example, for the path planning explanations, these ones, where you find changes to the model that lead to the expected path. So this can be done quite quickly. So first I had an algorithm that was slow, but you can always find ways to make it fast. And it takes like 1 second to generate an explanation. So it's quite quick for reasonably sized maps that you would use normally. But for example, for motion planning, for some kind of motion planning explanations, like if the reason why you fail is because you didn't wait long enough, you might actually have to wait a long time to resolve the problem for a long time and say, oh, in order for you to be able to say that you would need 2 hours to solve the problem, you might actually have to try and solve it for 2 hours. So for some explanations, it might take considerably long. For path planning, it's easier because since it's discrete, you can pre-compute explanations to a lot of different questions right from the beginning. You can leverage that. But for motion planning, continuous motion planning, some of them you might just have to say, if you want to do it quickly, you might have to skip doing some of the potential explanations, not investigate some of the potential explanations. Or you could say, well, if you want, I could also see if this is the source of the issue, but you would have to come back in a while, right? Yeah, but that's an important point.
Good, thanks. And then the second question, well, it's not a direct extension of the first one, but I was wondering your general framework for the kind of explanations, that you can expect from robot motion. Well, how generalizable that is to the tasks where a robot needs to interact with the human? Because the examples that you showed, it's just the robot and that moves, nice. But what if kind of a human is involved or several humans are involved? That's messy on its own, even without considering explainability. But if you want to add the explanations in terms of human sections, that also could come in very different shapes and forms. So how do you see this kind of generalization to human-robot interaction tasks.
Yeah, thanks. So I think, so even if your system is messy when there are humans involved, I mean, there will still be rules to how the robot should act, right? It is so if the user, of course, it's not as simple, but if this user is doing this, then I do this. So you can always, in this framework, you would still generate explanations by saying, by finding changes to the input, basically, that would lead to the expected outcome. So you could say, why didn't the robot do this while there were 3 people passing by and one operating that robot? And you could try and make simulations of removing one of the people, or putting one more person, or making simulating that the person who's controlling the robot asked for another command. So of course the space of exploration is huge, but I think the general framework of finding changes to the inputs of the control system, right, or the planning system, so that the things that were asked become true, right? So I think that's still valid. Of course, it will be more computational intensive and then potentially more difficult to interpret. So you'll again have to think about how to summarize this, or to figure out which are the relevant bits. But I think. I think it's doable. Yeah, I think there's a lot to be done. I think it's an interesting research avenue.
Yeah, me too.
Yeah.
That was fascinating. Thank you, Martin.
Yeah, thanks for the feedback.